Yeah, hello everyone. It's a pleasure to be here. Today we'll be shedding some more light into how Arbitrum is actually defended. So many of us have heard that Arbitrum is in a way defended through Ethereum, that it is through Ethereum that it is kept safe. But what does this actually mean? And why are we working on revamping the way this works? So most recently, we introduced Arbitrum Bold, which is a new protocol for Arbitrum chains, and more generally for optimistic rollups that is far more superior than what came before. So a big question is, of course, like where does Ethereum come into play in Arbitrum security? And a large part of it has to do with how Arbitrum state gets confirmed on Ethereum, right? Today, all the Arbitrum transaction data is actually compressed and posted to Ethereum and in things we call batches. So essentially, they're rolled up into a batch and posted over. And you can actually replicate the entire Arbitrum transaction history by looking at Ethereum itself. Arbitrum validators, so the entities that are in charge of protecting Arbitrum and confirming its states, actually post claims about these batches and attest to their correctness. But the main question is, okay, Ethereum doesn't actually know whether these claims are true or false, right? Ethereum receives some data about Arbitrum, but it's a totally different domain. It doesn't know whether somebody making a trade on GMX, for example, got the output that they claim they did. And at the end of the day, these are just entirely different systems with different states. So how do we actually figure it out? And Bold is here to help us figure out the truth. Within 7 days, the way it works is anyone can challenge a claim posted about Arbitrum to Ethereum and enter what is called a dispute or a challenge. And this is a game that is essentially played on Ethereum about this information. And within this period of time, anyone can come in. If somebody makes a false claim, they can dispute that. If an evil party wants to dispute a correct claim, they can also do that. And essentially, Ethereum is there, but doesn't know yet who is right. It's essentially like, imagine two kids are arguing about something that they broke downstairs, and their mother comes downstairs and asks, "Hey, who broke the vase?" And the sister says, "My brother did it." Brother says, "My sister did it." Okay, let's figure it out. So the cool thing is that because this game is played on Ethereum and Ethereum uses computation and is deterministic, the honest party will always win. So whoever is telling the truth about the state of Arbitrum will always be able to win any disputes against them. And this is why we say that honesty is the best policy here. The really cool part is that we only need one honest party in the world to be able to ensure that the funds are safe. And the thing that we're defending is actually the Arbitrum bridge. So the validating bridge is what we formally call it. However, a big problem is that today this game is permissioned. So if you want to play this game or you want to make claims about Arbitrum, you actually need to be allowed to do so by the DAO. And big question is, why is that? Why is it locked down? Why is it protected? The reason is the current system that we have today has a fundamental issue. So today, with this permission system, somebody could burn a lot of money in the form of stakes, and they could delay confirmations of Arbitrum as long as they're willing to burn this money. So this is a fundamental issue because we can't have guarantees on how soon an Arbitrum state can get confirmed on Ethereum. We want it to be within 7 days, but if there's a challenge, the current entity can just continue to burn more and more capital and cause greater delay. This will cause a whole variety of problems. So people won't be able to go back from L2 to L1, essentially withdraw their funds from Arbitrum. And it will lead to a lot of other problems in the sense that the chain is just not being confirmed, and the state is not being made canonical on Ethereum. So we devised a brand new system from the ground up called Bold, and it stands for Bounded Liquidity Delay. So what does this mean? Basically, it's a protocol that also defends Arbitrum, but actually guarantees us an upper bound on confirmation times. It's really nice in that it makes sure that even still, one honest party can win against any number of evil parties. And the best part is that somebody who wants to delay confirmations can't just pay more money to do so. They can't buy delay, basically. We bound it. And that's what makes Bold really special. Going down a little bit, so let's talk, what is a challenge protocol? So we've spoken about disputes over claims, we talked about challenges, and at the end of the day, what are we actually talking about? So more generally, it's a way for parties to dispute claims about computation. So they say, hey, I computed this state. And somebody says, no, I computed a different state. And we have Ethereum as the ultimate referee that figures out who was right or who was wrong. Right? Parties, essentially, they disagree over ranges of computation, because a computation on Arbitrum of the state transition can be very long. There can be a lot of steps involved. So the key thing is that they need to narrow down their disagreement to figure out exactly where the flaw is. So Arbitrum is programmed in the Go programming language, and it contains a state transition function that defines the logic of how Arbitrum processes transactions. This code, we turn it into assembly called WebAssembly, and challenges are actually over computation of this. WebAssembly is a really nice instruction format that is being adopted, has already wide adoption across major web browsers, and is being increasingly used in the server as a really nice compact way of representing computation. We've chosen WebAssembly already in Arbitrum Nitro, which has been live for a while because of these properties, and it also makes sense for something like challenge games. So essentially, what validators are arguing about is they're disagreeing over steps of execution in Arbitrum's WebAssembly state transition. Once somebody finds a single step of disagreement, so inside of this assembly, if we figure out exactly where there was a flaw, an honest party can submit a proof to Ethereum that can be verified in constant time and declare a winner. The way that it works in Arbitrum and how do you actually play this game is first, validators disagree over states. So on the right here, we have, okay, I say that the state at, say, block 0 is this, and then Alice says at block 4 it's this, Bob says it's something else. So clearly there's something wrong. These two entities are disagreeing over the state of the Arbitrum, over the Arbitrum chain. And it's clear the disagreement is somewhere between block 0 and block 4. So how do we actually narrow that down? And to do this, they need to basically play this challenge game and make what we call challenge moves. These validators, so let's say Alice and Bob, need to take turns to basically bisect their commitment. So bisecting is, okay, from 0 to 4, I'm going to bisect to 2. So divide that in 2, find the midpoint. And you're going to keep playing this game and doing basically a binary search until they figure out exactly the single block where they disagree. So once I figure out the block where I disagree, they can then narrow that down further into WebAssembly instructions. In bold, more importantly, not just Alice and Bob or Bob can make these moves, but anyone else can hop in. So for example, imagine if Alice drops out of the game, maybe their computer went offline or something else happened. You in your living room running a validator can join a challenge and defend against an evil Bob that might be trying to cause damage to Arbitrum. And that's the property that we really want to preserve and makes it really special to make it so that anyone can join into these challenges. However, let's say we found a single point of disagreement, a single block of disagreement. Inside of a block, we can have max of 2 to the 43 steps of execution. And we need to figure out exactly the single step of execution where we disagree. So that's a lot of information. That's very expensive. It's impossible to do it on chain, obviously. So what we do is that we play this game of bisecting and doing binary search over multiple levels of granularity. Essentially, we want to narrow down in a way that is efficient and gets us an answer really quickly. Doing it over 2 to the 43 is way too expensive. What makes Bold very special, once again, is that it does not suffer from these delay attacks. So nobody can come in and say, hey, I'm going to spend money and delay confirmations of Arbitrum on Ethereum. We have formal safety proofs of these delay bounds, which gives us a lot greater confidence in the protocol itself. And the nice thing is that a single honest Alice here on the right can defend against 10 or 20 or 30 or a significant amount of malicious entities. Because Bold is all versus all, meaning that the honest parties are all competing against the evil parties, we have a lot better guarantees than the current system. In the current system, challenges would be essentially one-on-one. So Alice against Bob, and they have to complete that. Then Bob against Charlie. Here, honest parties are competing as a team against everyone else. So one member drops out of that team, it's okay. As long as there's other members in that team, we can still complete a challenge. We also have a research paper that you can find inside of our Bold repository on GitHub that explains some of the internals. Now, let's talk about some of the internals of Bold for folks that are more interested in how it works. So at the core of the protocol is the notion of an edge. So what is an edge? It's essentially a commitment to some state. So what I say is that at block 0, I believe that the state root is this, and at block 4, the state root is that. However, we're just not committing to raw state roots. We're actually committing to the whole history. So the commitment at height 4 is actually committing to the entire history from 0 to 4. So it's essentially a Merkle representation of the history. When we bisect, so when we perform a binary search, the person making the move has to provide proof that the bisection is actually a prefix of the ending history. So you're telling me that, hey, this is the history that I believe is true. And if I want to narrow that down, I need to prove that the prior history is a prefix of the one that I just provided. So this keeps the protocol very safe because we're actually verifying, and you can't lie about a Merkle proof that is a prefix of another. Now, once we found out our single point of disagreement at a block level, we need to then go down into the assembly level. So as recall earlier, we discussed that in Bold, one has to play many different levels, many little sub-games to narrow down a single instruction. So here on the right, you can imagine with this magnifying glass, we're looking at a single disagreement at the top of blocks. Then inside of a block, we have ranges of execution. And inside of there, we have other ranges of execution. And we keep unraveling and unraveling until we figure out the single step of execution where we disagree. We call these games or sub-games sub-challenges. And to give them specific names, you can call them giga-step challenges, mega-step challenges, kilo-step challenges. So kilo-step, we're arguing over ranges of 1,024 steps of execution. And down until you find a single proof that somebody is incorrect. So what are some of the components of Bold? So Bold comprises two things. So first of all, we have on-chain smart contracts that can be deployed on Ethereum, but they can also be deployed on Arbitrum chains. So L3s could also leverage Bold. We also have the off-chain validator software. So this is actually code that you run outside, on your computer, and it connects to a chain endpoint and actually performs the responsibilities of being a validator. Today, Bold is fully compliant with the research paper. We've been audited by Trail of Bits. And fun reveal is we're actually running challenges today on an Ethereum Sepolia private testnet. And we're getting ready to make that private testnet public for everyone to run challenges on. Today, you can find us, it's fully open source. You can find us here at Offchain Labs/Bold. You can find our research specs, you can find documentation, you can find how it works. And great, so aside from the protocol itself, how does the actual software work? So you're running something on your computer that is defending Arbitrum. What is it actually doing? First of all, it needs to post claims about Arbitrum to Ethereum. So recall that disputes are over claims about Arbitrum. So somebody says, hey, I think the state root at this block is this. Somebody says, no, I think it's this. And they can challenge each other. Your validator software can also challenge others' claims. And most importantly, it can make moves, it can do bisections and perform that binary search to win against any number of evil parties. And the really cool thing about Bold is that there can be many challenges going on concurrently. So there can be a challenge going on right now, and in 5 minutes, there can be a totally separate challenge going on about a different claim. And all these things are happening at the same time, and Arbitrum can still be safe. We spent a lot of time making Bold very modular. So the repository is its own individual project that can then be plugged into Arbitrum Nitro with minimal changes. All we need from an Arbitrum node is access to the L2 state and proofs. Everything else we can handle ourselves inside of Bold. At a high level, you have this Arbitrum node here that has a bunch of stuff that it does. And we have this component that we just plug in called the challenge manager. This interacts with the on-chain Ethereum smart contracts to perform its responsibilities. And going deeper into the architecture, it does a bunch of other stuff, but it's all self-contained, and it all just needs a small API interface to the Arbitrum node to get the information that it requires. Awesome. So we discussed that the primitive in bold is something called an edge, which essentially is a commitment to some start and some end state. How do we manage this in the actual code? Because it seems to be quite complex, right? There can be many challenges happening at once. So the way we do so is we manage each edge in a single Go routine. So it's essentially a lightweight thread, a green thread inside of the Go programming language. And this allows us to handle many of them at the same time, and each edge is responsible for its sole responsibilities. It doesn't have to worry about what's happening in the greater challenge. Each edge in bold has a journey from creation to confirmation. So when an edge starts, it goes through a bunch of steps in a finite deterministic way until it reaches a confirmation stage. The goal is to make sure that each honest edge reaches the end state so that it gets confirmed. We call these finite state machines and how we manage this information. So you can imagine that many things around us and in our day-to-day life can actually be modeled using finite state machines. Basically, a series of states that have transitions between them, and you can follow very easily how to transition from one step to another and also prevent invalid state transitions from occurring. So in this example, we have this turnstile at a subway station, and you can imagine, well, in the older times, almost ancient times, we used to use coins. You would put in a coin, when it was in the locked state, transition to the unlocked state. You were able to then push the turnstile, it goes back to the locked state. If you push it in the locked state, it will be locked. So you can model a lot of very complex scenarios using state machines. And the most important thing is we can also model bold behavior using finite state machines. Gives us very nice properties and actually ways of preventing problems that would otherwise be really hard to debug. However, of course, the real world is error prone. So, something can fail, right? Maybe your Ethereum transaction can fail for whatever reason. Your internet connection might go off, and imagine you're tracking all these edges in your software. How does it actually make sure that it continues? Well, because we're using finite state machines, we can keep retrying the same state. So imagine we're trying to make a bisection move. If it fails, well, we just retry that bisection move. It makes modeling this behavior really easy when we use finite state machines. Eventually, we will have a path towards confirmation. More importantly, what if your actual node and your actual validator node crashes? So imagine that your power goes out at your house or something. Well, because we use, once again, finite state machines, we can always go back to the same state that we were in before the crash. So we make sure that everything is deterministic, and that's the way that kind of we make sure the bold software can always make progress. Another thing is concurrent challenges sounds really tough. So imagine there are many challenges happening at once. That seems like too much data to track, right? So for each edge, what do we need to keep track of? We need to keep track of their ancestors, their rivals, their timers, a lot of different things. And you can imagine a tree below that has a ton of different branches and quickly getting out of hand. So how do we fix this problem? Well, some members of our team, especially Chris Buckland and Mario, did a lot of work and a lot of really, really smart analysis to figure out that we only need to keep track of a single honest branch for bookkeeping. And actually, this still gives us the safety properties that we need for a challenge protocol. So we've done a lot of simplification and made things a lot easier to understand as a result of this. And the question is, for people that are probably interested in running bold, is it profitable? Are there gains to be made? Is it like Ethereum staking? And the answer is no, unfortunately. The bold protocol will refund honest validators through the DAO, ideally. And the DAO will hopefully give validators a small reward for defending the chain. But it's not meant to be a highly profitable activity. It's meant to be a way of defending the Arbitrum system. So participating in a challenge requires you to place a stake and also mini stakes for each sub-challenge. The sizes of these stakes are still yet to be determined. But at the end of the day, the most important thing is that it's easy to defend Arbitrum and that validators get compensated for doing the right thing. We have a private testnet already on Ethereum Sepolia that's successfully winning challenges. And we're proud to announce that we'll have a public testnet very soon. You'll be able to try it yourself and be able to try all kinds of different scenarios and see if you can break it, which we're very excited about. Aside from that, internally, we've been doing also more fuzz testing. So we do a lot of internal testing to try a variety of different scenarios. As we have both on-chain and off-chain components, we want to make sure that they work correctly. So we spend a lot of time on performance and making sure things are safe, making sure that we find bugs before they appear, and we've been making Bold more and more robust. Question is, okay, what's missing before a public testnet? Right now, we're in the process of trying more complex scenarios. So we want to test out more complex challenge games and sub-games. We're optimizing performance to make sure that people can run this at home and making sure basically all the loose ends are tied up before we make a public announcement. And the big question is, what's the road to mainnet? How can we actually get this live on Arbitrum 1 and take off the training wheels of permission validation? So the main thing is we need to propose Bold to the Arbitrum DAO. This, we believe, will happen very shortly after a public testnet announcement. And if this gets approved, we have to then upgrade an existing Arbitrum testnet to Bold. Once we have a lot more confidence, then we can upgrade Arbitrum 1 and Nova on mainnet. And yeah, so then again, you can contact me. My name is Raul. Once again, I'm here on Twitter, on Telegram. You can find us on GitHub, all over the place, and leaving you all here with a capybara. Thank you.
Thank you so much, Raul. It was really interesting to hear all about the Bold protocol. I'll open the floor for questions from the audience. Let's see if there's anything. I don't see anything right now. Otherwise, I'll ask a few questions myself, if you don't mind.
Sure, please do.
So you mentioned that it would be up to DAO to approve for the Bold to be integrated with Arbitrum 1 and Nova. So should the DAO approve, what are the risks that you think we should consider when integrating Bold into the actual proof protocol that we have right now?
Yeah, we anticipate that, the most important thing when proposing an upgrade like this is what can go wrong, right? And what will you do if it goes wrong? Is there a plan? Is there a plan B? Can you do anything? And yes, we have thought about a lot of these different scenarios. The most important thing is that Arbitrum has a security council, not just the Arbitrum DAO. So the security council, can step in case there is a extremely serious problem. So one of the things that could go wrong is that there's a bug in the one-step proof where an evil party can say, hey, I submit a proof and that proof is wrong, but there's a bug in our code that thinks it's correct. So the Security Council actually has 3 additional days, or actually it's a configurable parameter, but they can step in and they can say, no, there was a faulty one-step proof. We can have some intervention. And this is in a disaster scenario. Once there's a lot more resilience in Bold in production, we can remove a lot of these training wheels. But it is important that as it goes live, there are stopgaps in the beginning to make sure that it is safe.
Amazing, thank you. And how confident you are, the whole team that is working on Bold, in the safety of the Bold protocol?
Yeah, we actually feel very confident in a few different aspects. So we feel confident in that the off-chain component of Bold, so the Go side, is actually getting a lot more robust over time. And the most important thing is that if there's a bug there, it's not the end of the world because we can easily upgrade that software. If there's a bug in the Solidity side, then that's more problematic because that would require upgrading the contracts and possibly invoking the Security Council. So with the contracts, we spent a significant amount of time on auditing with Trail of Bits. We spent a lot of time on testing, on making sure that we have a variety of different scenarios, making sure that the system cannot get into an invalid state. But a lot of the time that we spent over the last few months has been in hardening the protocol against a variety of potential attacks. So we feel good about where we are today. We also feel better about the fact that we have these systems in place in case things go wrong.
Amazing. Thank you very much, Raul. I don't have any question myself, and I don't see anything in the chat either. So if you don't have anything, we can wrap this up here.
All right. Thank you so much, everyone. Have a great rest of the day.